Good day, everyone. I am John Brian Almazan, presenting to you the angular modulation. So, angular modulation is the process in which the frequency or the phase of the carrier varies according to the message signal. So, the general expression of angular modulation is given by V of t is equal to E sub c times cosine of omega c t plus theta of t, where V of t is the angle modulated wave, E sub c is the peak carrier amplitude, F sub c is the carrier frequency, and theta of t is the instantaneous phase deviation. This is further divided into frequency and phase modulation. So the frequency modulation, the frequency rather than the amplitude of the carrier wave is made to vary in proportion to the varying amplitude of the modulating signal. The carrier amplitude remains constant, but the frequency is changed in accordance with the modulating signal. Thus, the higher the amplitude of the information signal, the greater the frequency change. So the phase modulation is a modulation technique in which carrier phase varies based on analog baseband information signal to be transmitted using wireless device. If a constant amplitude as well a constant frequency sine wave carrier is given to the phase shifter, the output is phase modulated signal. Phase modulation is referred as indirect frequency modulation due to the fact that phase modulation produces frequency modulation. For the comparison between amplitude, frequency, and phase modulation, all these modulation types are analog modulation techniques. All the modulation types are used in transmitting information from one place to another distant place. Mostly, these techniques are employed in wireless communication. In terms of function, the amplitude, the frequency, or the phase of the carrier wave varies as per voltage of the modulating signal input for amplitude modulation, frequency modulation, and phase modulation, respectively. In terms of carrier parameter, the frequency of the carrier wave is kept constant for amplitude modulation, while the amplitude of the carrier is kept constant for frequency modulation. For the phase modulation, the amplitude is kept constant. Time domain of FM and PM signal. The peaks are slightly closer together when the baseband signal is near its maximum value. So we do have frequency modulation here. The problem is that the baseband variation are not producing enough carrier frequency variation. We can easily remedy this situation by increasing the modulation index, and by doing so, the frequency of the modulated carrier continuously tracks the instantaneous baseband value. Frequency domain of FM and PM signal. It is interesting to find that AM and narrowband FM produce similar changes in the frequency domain. The narrowband FM involves a limited modulating bandwidth and allow for easier analysis. In both cases, a low-frequency spectrum, including the negative frequencies, is translated to a band that extends above and below the carrier frequency. For the FM modulation index, it is the ratio of the frequency deviation to the modulating frequency, which is given by beta sub Fm is equal to delta F over F sub M, where beta sub Fm is the modulating index, delta F is the frequency deviation, and F sub M is the modulating frequency. So the modulating index of frequency modulation is derived by simplifying the general expression of FM wave, which is given by x sub Fm of t is equal to E sub c sine of omega ct plus k sub f times 2 pi multiplied by the integral of the modulating signal from negative infinity to t. By simplifying that equation and integrating the modulating signal E sub m of t, it will yield to the simplified expression of the FM wave where the modulation index will be derived, which is highlighted with the red font. For PM modulation index, it makes the phase variation more or less sensitive to the behavior of the baseband signal, which is given by beta sub PM is equal to K sub P times E sub M, where beta sub PM is the modulation index, K sub P is the constant known as phase sensitivity, and E sub M is the amplitude of the modulating signal. The modulation index of phase modulation is derived by simplifying the general expression of PM wave, which is given by x sub PM of t is equal to E sub c cosine of omega ct plus k sub p multiplied by the modulating signal. By simplifying that equation, it will yield to the simplified expression of the PM wave where the modulation index will be derived, which is again highlighted with the red font. The FM percent modulation is the ratio of the actual frequency deviation to the maximum frequency deviation multiplied by 100. For frequency deviation, it is the maximum difference between the FM modulated frequency and the nominal carrier frequency, which is given by delta F is equals to K sub F times E sub M, where delta F is the frequency deviation, K sub F is the frequency sensitivity, and E sub M is the amplitude of the modulating signal. Considering the modulating signal given by E sub m of t is equal to E sub m cosine of omega mt, and the frequency of FM signal given by F sub I of t is equals to F sub c plus K sub f times E sub m of t. Substituting the modulating signal to the frequency of the FM signal will produce an equation where the product of the frequency sensitivity and the amplitude of the modulating signal is the frequency deviation. The maximum or minimum frequency deviation can be determined by adding or subtracting the frequency deviation from the carrier frequency, which is given by carrier frequency f sub c plus minus the frequency deviation delta f, respectively. For the phase deviation, it is the maximum difference between the instantaneous phase angle of the modulated wave and the phase angle of the unmodulated carrier, given by delta theta is equals to K sub p times E sub m times F sub m, where delta theta is the phase deviation, K sub p is the phase sensitivity, E sub m is the amplitude of the modulating signal, and F sub m is the modulating frequency. Considering the general expression of the PM wave, simplifying it further will produce an equation where the phase deviation can be derived by getting the product of the phase sensitivity, the amplitude of the modulating signal, and the modulating frequency. By dividing it with the modulating frequency, modulation index can be solved. So the deviation ratio is the ratio of the maximum carrier frequency deviation to the peak modulating frequency. Considering a frequency modulation equation given by E sub Fm of t is equal to E sub c cosine of omega ct plus m times sine of omega mt. A trigonometric identity cosine a plus b can be applied to it so that it would be simplified into an equation which contains a trigonometric series called Bessel function. Having the derived equation of the frequency modulation a while ago, it can be expanded using Fourier series, in which the Bessel function was further simplified and expanded. Substituting those two expanded Bessel function to the Fm equation will yield to another expanded equation of the frequency modulation equation, which is the equation at the bottom part. Having now the equation of the frequency modulation, which consists of the expanded Bessel functions, applying the Bessel identity, j sub negative n of m is equal to negative 1 raised to n times j sub n of m. The frequency modulation in Bessel form will be derived, which is E sub Fm of t is equal to E sub c multiplied by the summation of the product of j sub n of m and cosine of omega c plus n omega m t. For the practical bandwidth calculation for frequency modulation, it is given by 2 times the quantity of m plus 1 times f sub m, where m is the modulation index and f sub m is the modulating frequency. So these are the references that was used in the discussion. So that concludes my presentation. Once again, I'm John Brian Almazan. Thank you.